Welcome to the How to Use Component Maps tutorial. This tutorial is part of the tutorial series dealing with more advanced topics on the use of the gas turbine performance software GasTurb. In this tutorial, we will take a closer look at how to use component maps in GasTurb. We will focus on compressor maps. However, all the presented functions are applicable to turbine maps as well. We will start with how maps are scaled in GasTurb. We will investigate how GasTurb uses scaling factors and modify the scaling reference point location in a compressor map. Finally, we will learn how to edit the compressor map to match our simulation with loaded test data. For this tutorial, we will use a single-spool turbojet engine. We select the turbojet from the Jet Engines tab and choose the configuration without afterburner. We click on Off Design to open the Off Design Point input window. For now, we leave all input data as they are. Let us first take a look at the compressor map. The compressor map is used for the simulation of off-design points, as we have previously discussed in the Introduction to Off-Design Simulations tutorial. The off-design point corresponds to the design point at a corrected mass flow of 32 kilograms per second, a pressure ratio of 12, and an efficiency of 85%. This is expected because we have not changed any input data yet. This compressor map is the standard map included in GasTurb. It is scaled according to our chosen input data, such that the scaling reference point of the map corresponds to the cycle design point. In many cases, the standard map yields reasonable trends. In other cases, depending on the machine type and design, for example, if a centrifugal compressor is used, a different map should be used to accurately predict operating behavior. Let us now look at how to select a different map. We close the result window and choose Maps under Maps and Connections. The Component Maps window opens. Here, we can check and adapt the map for each turbomachinery component of our engine. On the top, we can switch between the different components. In case of the turbojet engine, we only have one compressor and one turbine. On the right, we see the selected components map. The map is shown in its unscaled form. The map scaling is only applied when calculating off-design points, and the scaled map is therefore only shown in the off-design result window. On the left, we have options to change the current map, and we can see information on the map scaling. Let us begin with how we read a new map. The GasTurb software comes with maps from open literature for various machine types. These maps are selected using the drop-down list on the left. In this case, there are maps available for axial compressors with different pressure ratios, as well as for 1- and 2-stage radial compressors. Alternatively, we can read a different map. For example, if we have a map of our component in question available in the GasTurb file format. For the sake of simplicity, we will continue with the standard HPC map. To get a better understanding of the usage of maps, let's first take a look at the format under which maps are stored in GasTurb. In the given map file, the necessary data for mass flow, pressure ratio, speed, and efficiency is stored in tabular form. As coordinates the speed lines and auxiliary coordinates, the beta lines are used. As explained in the tutorial, Introduction to Off-Design Simulations, the beta coordinates help us to avoid convergence problems in regions of low and high corrected speeds, where the pressure ratio and mass flow relationship often becomes ambiguous. For each coordinate consisting of a speed and a beta value, the associated mass flow, pressure ratio, and efficiency are defined in the map file. For any off-design point, the map values are then interpolated within this given data. GasTurb scales the given map such that the input design point is matched with the map scaling point, which is marked with a yellow square. By default, the scaling point of the standard map is at a pressure ratio of approximately 8.3 with an efficiency of 0.86. To match our actual compressor design point, the map is scaled accordingly. On the left-hand side, the corresponding scaling factors can be found. The P over P minus 1 scalar fits the pressure ratio of the design point. In this case, it is 1.504 to match the pressure ratio of 12. The efficiency of the map must be adapted as well. The efficiency scaling consists of 2 steps. The scaling of the whole efficiency value table according to the dictated scaling factor, and the Reynolds correction, which accounts for the influence of the varying Reynolds number. The Reynolds correction is only of secondary effect. Details on the calculation can be found in the manual. Here the efficiency scalar is 0.9884, such that the design point efficiency value of 0.85 is matched. The efficiency scalar affects the whole map. Accordingly, also the peak efficiency within the map changes. The maximum efficiency of the scaled map is shown as peak efficiency. Finally, the coordinates of the scaling point within the given map are displayed. The position is specified by a relative corrected spool speed of 1 and a beta value of 0.5. Often it is necessary to change the location of the scaling point of the map, as for example, the design point demands a higher surge margin than obtained by the current scaling point location. In order to change the position of the map scaling point, we need to adjust the coordinate values. We can either input the desired values or we can relocate the scaling point within the map via using drag and drop. Let's change the position of the scaling point to a beta value of 0.4 and a relative spool speed of 1.05. The pressure ratio and the efficiency in the map are different for this map scaling point, as the demanded conditions of a pressure ratio of 12 and the efficiency of 85% remain the same. The scaling factors are automatically adjusted. In some cases, we might have a map available which we do not want to scale but use as it is. This is accomplished by selecting Do Not Scale this map. Further information about the usage of unscaled maps can be found in the manual. Let's close the Component Maps window. Now we run an operating line calculation. We leave all input data with the default values and do not add another operating line. Let's take a look at the compressor map. We can now observe the scaled map we defined in the Component Maps window before with a different scaling point. The efficiencies are assigned to higher values, and the mass flow is adjusted compared to the previous map that was scaled with default settings. As the reference value of the relative spool speed is the dictated design point condition, the speed line passing the design point has the value of 1. The values of the other speed lines are now scaled according to the changed scaling point value. Now let's draw the graph Specific Fuel Consumption over Net Thrust. As a comparison, in gray color, we see how the same curve runs if the compressor map is scaled with the default scaling point. Both simulations were conducted for the same design point, which is also the reference point for map scaling. Therefore, both simulations give identical thrust and fuel consumption values at this point. The scaling point relocation strongly increased efficiency through a wide range of the compressor map. The specific fuel consumption is consequently much lower during off-design operation. This underlines that when analyzing off-design behavior, the map and the reference point for map scaling should be chosen wisely. Let's return to the off-design input window. In some cases, test data of an engine may be available, and it may be desired to match the simulated behavior in GasTurb with this data. To do so, GasTurb offers a convenient tool to adapt the component maps. Let's reset our scaling point selection and start another operating line calculation. This time we click on Compare, read and select the test file demo_jet.tst with the measured data. Now we run the operating line calculation. We draw the picture specific fuel consumption over net thrust. The option to add the loaded test data to the graph via Show Test Data is by default yes. Besides our simulation results, we can now also see the loaded test data marked with gray circles. We see that the test data does not match our simulation results at part load. Let's click on New Picture and plot the isentropic compressor efficiency over the corrected compressor flow. The efficiency values of the compressor map are too low in part load. To improve the agreement, we can now edit the HPC map data with a dedicated tool that comes with GasTurb and can be found under the Compressor Maps group. Edit Compressor Map. This tool allows us to adapt the compressor map such that the efficiency, the mass flow, and the pressure ratio of the calculated operating line match with the loaded test data. We will start by matching the efficiency values. On the left, there is a list of the original peak efficiencies for every speed line of the map. These values of the original peak efficiency are shown in the diagram on the right as well. Additionally, the efficiencies along the operating line and the measured efficiency data points are shown. We can now adjust the efficiency values of the original map such that the operating line efficiencies match the test data. For that, we can edit the peak efficiency values individually in the list on the left or change them all together by moving the slider on the right. While moving the slider, the values in the third column change, except for those where the checkboxes are checked. We first only look at the lowest speed value and move the lines with the slider to the optimal position. Then we fix that delta peak efficiency value by clicking the checkbox. We continue this procedure until we reached a good match between the test data and every point of the operating line. The data point at the cycle design point needs to remain the same and is therefore fixed, as otherwise the correlation with the map would be affected. When comparing the compressor map before and after the adjustment, we can see that the efficiency values changed within the map towards higher efficiencies at low corrected speeds. After adjusting the efficiency values of the map, we close the compressor map editor and write the new compressor map to file as HPC01_V01. Besides storing the modified map itself, we should also save our model as an engine model file to save the reference to the newly created component. Note that to store an engine model file, all input data in the steady state page need to be identical to those from the cycle design point. After saving the engine model file, let's recalculate the operating line. As the compressor map changed, we obtain a new operating line, but the data still do not match, especially in part load. We open the compressor map editor again. After having adjusted the efficiency values of the map before, we will now adjust the mass flow via the Speed Flow tab. There are 3 lines in this picture. One for the lowest corrected flow in the map with the auxiliary coordinate beta equal to 1, a second line representing the maximum corrected flow in the map with beta equal to 0, and a line in the middle representing the corrected flow for the current operating line. In the table on the left side, the original speed values are given. We can relabel the speed lines by editing the numbers in the second column of the table or by using the slider below the figure. We continue with the same procedure as for the efficiency values using the slider tool and try to find a good match of the operating line with the test data. After recalculating the operating line, we see here that further adjustments are necessary. We can further improve the agreement with our test data by iteratively editing the map and calculating the operating line. In this case, after a second adjustment of the efficiency values of the compressor map, we obtain a good agreement between the simulation results and our loaded test data. This concludes the Component Maps tutorial. We learned how to use component maps in GasTurb and how they are scaled according to our design point location. We further learned how to work with special maps and to edit any compressor maps for matching the simulation with test data. With these powerful functionalities, GasTurb enables us to quickly gain an understanding of the gas turbine's operating behavior. For more detailed information on the use of component maps, the GasTurb manual offers extensive guidance. There are further tutorials covering a wide range of GasTurb's tools and functionality. Pick any tutorial that you are interested in. We hope you have a great experience using GasTurb. In case of questions, don't hesitate to contact us.